Hi, I'm Guo Cheng Guang, 12 years old, Secondary 1 from NUS High School. Right now here in this lesson, we're at theoretical mechanics. Well, theoretical mechanics, right now here, still going on with our first chapter, or chapter 1, kinematics. For this type of kinematics, from the last lesson, I'm just going to say a little bit more about, like, if you want to find the direction, there are also different ways of representing it. So I'm just going to show one more way that you may want to represent it as in this lesson for the first part. After that, I'll just go on with the other accelerations. So right now from here, first of all, when you get this vector, this r vector from here, you may change it into r. This is just taking that value from this vector, then it times an r unit vector. So this unit vector is telling you in which direction this vector is. And this r, you may write it as a vector with extra modulus. Okay, so that's what you may get from here. So from this part that we get, let's just have an example. So this example here, let's just say we have 3i vector. Well, I vector is a unit vector. And this unit vector is in the direction of x. Then you add for j vector. Now j vector is another unit vector. And this unit vector is in the direction of y. And then this is equal to, well, if they want you to find this part, I'm just going to draw out how, if they want you to find this, how you can find it. So for example, let's just draw one part here. Okay, you also have to, at the same time, be aware of where it is. So in this part, x direction, well, let me just like draw the whole x-axis so that you can be more sure of this. So x and y. So then we have 3 units in this x direction. Let's say this 3 is here. They get 4 units in the y direction. So let's just say it is around here. So then afterwards, you connect these parts, then what you have at last is this vector times this length. Well, you're just using the Pythagoras theorem. 3 square add 4 square root, that's a 5. Then your direction. You cannot miss out this direction here. All these in front, they have a direction. This definitely have a direction. So this direction, we can just use the unit vector of r. Okay. Then, as I said, you want to represent this in a different way. Well, at least a little bit different. Let's use this part above. So we have this entire vector. Then you over r. So in this part above, well, you can just take it as this previous part. This previous part actually just saying about this vector already. Then afterwards, r. R from this part, we're just only taking down this value. So we're only taking down the value. That means what we get is the 5. So that's what we have here. Alright. Well, let me just tell you that this way of representing that I'm going to show you, well, we're going to use cosines to represent it. So in this part, there is a cosine alpha. Well, this is with the x-axis. this part will be for our alpha. Then, of course, here in the x-axis. Then after that, since you also have one that goes to the y-axis, we're just going to mark it with a beta from here. So that's what we have. And don't miss out that this is in the y direction, so j vector that you have there. Well, let me just tell you that this type of representation, well, we can just call it the directional cosine since we're using cosines. So from this part, well, we're just using 2D in this. We're only using 2D, well, just to tell you more 3D, if you want 3D. So your direction here will be still there's an alpha. Well, let me just tell you, like from your line, from the vector that you have, if it is in 3D, so from this part goes the angle with the x-axis, then cosine beta. So it is the angle with the y-axis is beta. Then we have a cosine gamma. So cosine gamma is just this vector, the angle it makes between this vector and the z-axis. So that's what you'll get if you have 3 dimensions. Well, if you want to say like you go on, well, like 4 dimension or whatever you think of, it just goes on in this way. Okay, so that is the part that we have here that I actually wanted to add on. So this, we're calling it directional cosines. Just a fun fact. Square of this part in front, square of this in the middle, and square of the last part. Just a fun fact, it is actually equal to 1. Well, then you just suddenly like think of sine squared and cosine squared. So from this part over here, let's get into the actual this lesson's what we're going to learn about. So from this lesson right now here, so we're already starting on acceleration. And acceleration, we do have different types of acceleration. But in this time, what I'm going to start with acceleration is, let's look at this graph that we have here again, or these drawings, or whatever you call it that we have over here. So first of all, this is still about circular motion. Circular motion. And it is uniform speed. Uniform speed, you have to be really careful of that. And from these parts, this radius, it is also fixed. So uniform speed, fixed radius, so that it don't go out or it don't go in. Okay, so that's what we have here. So this radius to both. Then here, this lines that extend out that you see here is actually your tangentials. So those are your tangentials. Then next, let's take a look here. Now, this is the original circle, the whole thing that we have. But what's this part here? What's this part here that we have? We just straight away take these tangentials down. And like we form a triangle with like 2 of these tangentials. Well, how do we actually find that? Well, from this part, we're just like drawing a parallel line. Well, we can find it. Wait, let me just connect these 2 first. So wait. So from this part that you have here, if you connect these already, then you get 2 triangles. But then we try to find a relationship between these 2 triangles. Or how do we actually find it? So firstly, this triangle that you have here is an isosceles triangle. Then after that, from this part, well, v1 vector, v2 vector, since it is uniform speed, that means these 2 are also equal. Okay, but you have to be aware just only the length for these two are equal. Okay, so we found that these two are actually isosceles. Then we need one more angle. So this angle we've already known, it is theta. But wait, how do we know that this angle, whether it is theta? So let's just see. This part, let's just take it as like a solid that it looks something like a feet. Then after that, it swings up, but it cannot move. It only swing about. And then that means, well, for this part, this kind of thing that you say it is that this thing is what you call it a rigid body. So this is just rigid. So when it swings up this angle, theta, this part also moves up, theta. Okay, so then we do have these two isosceles triangle here. Let me just write it down. That means triangle OAB will be similar to triangle you're of this part O prime, A prime, B prime. So that's what we have here. We found that these two triangles, both isosceles triangle, these two triangles are similar. So definitely then their side ratios, corresponding sides, or within their own triangle are similar. Well, the ratios are equal from this part. So what if we take OB over AB? Like at the beginning, you may just be like experimenting about. Then you just take this value. Well, at the same time, we're just still trying. So then you have to equals be what corresponding sides from this first part O prime, B prime over. So O this AB, you get A prime, B prime. So that's what you have here. All right. From this part, let's try to find what is OB. Well, OB we're given R. So R is what we have. AB, do we know what's AB? But beware, it is the chord AB. It is not the AB. Well, AB, we don't know about it. So let's just leave AB as it is. But just beware, we're just adding this bar on top just to tell ourselves that it is a chord. Then it is equal to O prime, B prime. These two are equal, these two lengths are equal, but their direction is not the same. So we're just taking V for that. Since this is telling you about their tangential speeds, tangential velocities, but only their value is the same. So we're just taking V for that. Then you go over. So A prime, B prime, from what we have here, we're having it as delta V, but only V is this vector. Let's say we just directly write it like this. Would it be equal? Let's see. This side you have a vector here. This side you don't have a vector, so it's definitely not the right thing. So to make this a scalar, you put magnitude or modulus to take only its value for this part. So that's what we get here. Then next, this thing that we do have over here, what if we move it to the other side? Then after this one, we get on the remaining. Okay, so this is what we have. So then from the next part, let's take a look. Here we have delta, V vector, then modulus. So that, okay. What if we're just like a little bit of experimentation, then we just try it over a delta t. And of course, from this part, wait. So from this part, we're just going to try to let this be a limit. This limit, delta t, well, from this part approaches 0. Delta is part above over a delta t. Delta equals, so the other side you also have to do the same. Then from this first part here, now what can we get? Well, let's just say that we change the form a little bit. We change this form a little bit. It becomes this whole thing, you take the modulus. Now from this part behind, you take out v over r. Since this v is already the same, since there's no acceleration, then this r, well, it is given that it is fixed. But this AB here, right now, we can either take it as the chord, or we can also take it as this arc here. Well, how is it possible that we can take it as chord, we can take it as the arc? Well, from here, since this time that your given is very short, then as you get this part, yeah, let's say for example here. At first it may be like this, then after that gets smaller. Then from here what you see it will be that it's just like it completely overlaps. Then when it overlaps, that means it is the same. So that's why we can take it as either as a chord, we can also take it as the arc here. So next, let's see. From this part over here, what we get from here? Let's take a look. So all these delta, well, we can just straight away change them to these, okay? Because this limit delta t approaches to 0. Well, in this part that we have v, it can stand for velocity, it can stand for speed. After it gets differentiated, you get acceleration. Well, in fact, this is a definition for acceleration. So that's why you get a here. And since vector, then modulus, so then you won't get another vector here. And then from these parts, it is going to here. But since we drew parallel lines to these, and then we try to find it last. Well, it points to the center. And in fact, if you have drawn a lot more of these, at every single position, it points to the center. So then it's every time it's a different direction. And that means, well, from here, it always a different direction. So that's why we, at the center, that's why we can only have a scalar value for this. It cannot be a vector, since at every position, the vector will be different, since different directions. So this one, the part in front. Then this will be equal to AB arc. Arc AB, this part, if it goes very small. It goes very small. So what happens at last to this arc is that you can just take it as delta s. Well, since you have this limit, you just take it as ds. That's what you have. And that means it will just become v. So that means this is equal to a v squared over r. And if you could recall about what we have learned a long time ago, well, for that is the electricity. Well, electricity, we have power. And those powers, Well, there's one form which represents the power. It looks something like this. So at this part over here, that's what we have. This and here, well, you can just call it the normal acceleration, normal, or the centripetal acceleration. So that's what we have. Well, let me just say about some other things right now. It's already the acceleration. So the conditions for this part, well, at least this example that we have, uniform speed. Now, uniform speed, what do we think of? So from here, at least here, V1 is equal to V2. Well, beware, they're taking a modulus, which is taking a length. So this is a V. So then we'll just use it as a C. But how about let's put it as C1 first, from this part. Then after that, so here's already your V. So here's speed. Well, from this part, is there any of this? Well, this becomes acceleration. So is there any of this acceleration? Well, you don't have acceleration since this is the uniform speed. So of course you don't have acceleration here. How about d theta dt? So this is the angular speed. Well, angular speed, you do have it. You do have angular speed. So that's why here I put it as C1 first. Here is your C2. So that's what you have here. Alright. Well, is there any way that we could link C1 and C2 together? Well, let me just tell you that this is actually omega from this part. Angular speed, omega. And if it continues differentiating, you get another 0. So you have to be aware, since this is uniform speed, these two, well, they are both 0. So V and this omega over here. Is there any ways to link them together? Well, actually there is. Just by S being equal to R theta. S equals R theta. So that's S from this part. We're using C1. Then after that, R here, well, we don't know its value. Then theta from this part, we're just going to use C2. So this is actually that relationship between these C1 and the C2. So far in this lesson, I hope that you're clear so far. So I'm just going to end this lesson here. So if you like our videos, don't forget to subscribe to our channel. We'll see you in the next lesson. Thank you for your watching.